Let's talk a little bit about what is color. Looking at the screen right now, what do you see? What do you think you see? Seems pretty straightforward, right? You see a white circle on a black field. Or do you? There's actually nothing white on that screen. There are 3 circles. You can see them breaking apart here. One of them is red, one of them is green, one of them is blue. Those are the only 3 things that are actually being generated by the computer. Your eye does some amazing things, and amongst the amazing things it does is it lies to you about color. So here where you see the red and the green overlapping, you think you see yellow. Here where you see the green and the blue overlapping, you think you see cyan. And here where you see the red and the blue overlapping, you think you see magenta. But in fact, there are only 3 colors on the screen: red, green, and blue. The fact that they all mix together to form what you perceive as white is due to the way your eye works. So let's take a look at that real quick. The inside of your eyeball is covered with a lining called the retina, and the retina is covered with cells that sense light. Now, most of your eyeball is covered with structures that are called rods. Rods are sensitive to light, but they're not sensitive to color. They detect brightness, and they detect brightness at a wavelength of about 498 nanometers. In the very back of your eye, right in the middle of the retina though, there's an area called the fovea. And inside that area are structures called cones. There are 3 different types of cones. Each one is sensitive to a different wavelength of light: 240 nanometers, 534 nanometers, and 564 nanometers. Okay, so what exactly does that mean? Let's talk a second about what is light. Light, what we call visible light, is a very small subset of a much larger spectrum, the electromagnetic wave spectrum. It's composed of photons, little massless particles that zip through the universe at the speed of light. But not only are they zipping forward through the universe at the speed of light, they wiggle from side to side as they travel. How quickly they wiggle is a measurement of how much energy they have. So photons that wiggle very slowly are actually what we call radio waves. Radio waves that wiggle very slowly have incredibly long wavelengths, sometimes kilometers long. It takes kilometers for the particle to wiggle from one side to the other and back again to complete one cycle of the wave. As they get more energetic and wiggle from side to side more quickly, we start getting into microwaves. As they get even more energetic, we start to approach infrared light. And again, as they wiggle even faster, we start moving into the range that we consider visible light. But it doesn't stop there. As they keep getting more and more energetic, as they wiggle from side to side ever more quickly, they move up into the ultraviolet spectrum where we can't see it anymore. From there, they actually head into X-rays and then on into gamma rays. This is kind of crazy, isn't it? The very same thing that makes your car radio work is the same thing that heats your food in a microwave oven, is the same thing that warms the spam musubi in the 7-Eleven. It's the same thing that lets your eyes function. It's the same thing that lets the doctors take an x-ray of your hand. It's the same thing that turned Bruce Banner into the Incredible Hulk. It's all just photons, just different levels of energy inside a photon. All right. We can measure photon energy a couple of different ways. We could totally measure it in frequency the same way we do with audio. But because the speed of light is so high and because these guys are wiggling back and forth so fast, measuring it in hertz just gives us silly large numbers, right? Visible light would be a 1 with about 15 zeros after it, hertz. That's kind of large number to use. So what's more practical is we will just chop it up into the length that the photon travels as it completes one cycle, the length of a wave or wavelength. Again, down at the radio end of the spectrum, a wavelength can be 100 meters or more. It can be the length of a soccer field for that photon to make one oscillation. It can be much longer. It can be kilometers long. By the time we get to the wavelengths that your eye responds to, nanometers is the best way to measure this. A nanometer is 1/1 billionth of a meter. That's right. If you cut a meter into 1 billion with a B pieces, we're going to use those tiny, tiny units to measure the wavelength of light as we perceive it. The human eye can perceive light from a long wavelength of about 700 nanometers to a short wavelength of about 400 nanometers. Now, those numbers that we talked about earlier, 564 nanometers, 534 nanometers, 420 nanometers, the wavelengths at which the three different cones in your eye are most receptive correspond to what we call red, green, and blue. So literally, the back of your eye has got sensors that are picking up these very specific wavelengths, and your brain is interpreting them into this thing that we call color. And you can only see three of them. You only have the equipment in your eyeball to see red, to see green, and to see blue. Any other color you see is your brain doing processing to mix those colors together, and it's lying to you. Interesting sidebar, not everybody has exactly three sets of cones. People who are colorblind, and most of those people are male, you've heard this term before, colorblind, are actually lacking one set of cones. They only have two sets of cones, so they're actually only perceiving two of what we call the three primary colors. Another subset of people, most of these are women, actually have a fourth set of cones. They perceive an additional set of wavelengths that the rest of us don't see. And it's actually nestled in between the red and the green, where those are most sensitive. They can see shades of orange that simply don't exist to most of us. Apparently about 12% of women have this condition, roughly the same percentage as the number of men that have color blindness, which is kind of unfair. But there you have it. So maybe you've heard all your life that the primary colors of red, green, and blue. Maybe you've never heard that before, but certainly you've seen computer games and editing software and monitors that talk about RGB, and you've played with colors based on an RGB scale. This is why red, green, and blue are considered the primary colors of light. It's the three wavelengths of light that our eyes are built to receive. Everything else is an illusion, which is pretty cool, or pretty weird, depending on how you want to look at it. Now again, looking at our three colored circles, I promise you, I made this on Adobe Premiere. There's a red circle, there's a green circle, and there's a blue circle. There is nothing else. There is no cyan, there is no magenta, there is no yellow, there is no white. There are only three colors on this screen. Everything else that you see is your brain lying to you. Here's another example. I've got a close-up shot of Buzz Lightyear here, but look what happens when I separate out the three primary colors. There is no full color version of this on the screen. There's a red only, there's a green only, and there's a blue only. But when you put them together, you perceive an entire range of colors from those three. Another interesting sidebar, purple, magenta, that entire spectrum is a lie. It doesn't actually exist anywhere in nature. You can look along the continuum spectrum of light here. If you look halfway between blue and green, you can see where cyan would be located, and you can assign a wavelength number to that. If you look halfway between green and red, you can find yellow, and you can assign a wavelength to that. But if you look halfway between blue and red, you don't find purple, you don't find magenta. You find something in the green range. There is no wavelength of light that is magenta. There's no wavelength of light that's purple. This is your brain doing a phenomenal amount of lying to you about what it's interpreting, what it's seeing. But you're taking these two disparate colors that are on opposite ends of the visible spectrum from each other and perceiving something that really doesn't exist, which is also kind of a cool thing. All right, what are we going to do with this? Moving forward, we're going to talk about color correction. I'm going to do this in Adobe Premiere, but the principles would be the same in any software that you're working with. And we're also going to talk about some other fun things with how your eye works and how video relates to how we fool your eye into thinking it sees something that's not real.